Section 6.1 will be the most heavily tested in this chapter. We're going to discuss the topics of standardization, and this will involve a review of z-scores, and then the relationship between z-scores and percents or probabilities, and this will be the StatCrunch calculational part. All right, let's start out with the concepts. This word standardization is very important, so let's discuss what that means. Any normal distribution can be standardized with z-scores. Standardization basically means to take many different disparate distributions and make them look the same in a certain way so that we can compare them to each other. And we've seen formula for the z-score before. We're going to come back to this in a moment. But I want to illustrate what exactly they're for first. So example 1 on your handout here gives you two distributions that seem like they have they don't. They have nothing in common. But we're going to see that there is some underlying mathematical similarity that has to do with how they're distributed. Okay, so the weights of beans in cans of Bobby's Baked Beans are normally distributed with a mean of 16.0 ounces, symbolized by mu, and a standard deviation of sigma equals 0.1 ounces. Okay, meanwhile, in Durango, Texas, office workers have commute times that are normally distributed with a mean of 14 minutes and a standard deviation of 2 minutes. Okay, so these distributions involve completely different things and measurements. This one measures ounces of beans, this one measures minutes of commute time. But what they do have in common is their mathematical structure. They're both normally distributed. Consider this question that might seem absurd at first glance. What does a 16.2 ounce can of Bobby's Baked Beans have in common with a Durango, Texas worker who commutes for 18 minutes? Wow, this class is getting really weird. Okay, so let's take a look at these two distributions. And this gives me a chance to use my little markup tablet. So what we saw with Bobby's Baked Beans is that the mean is, I guess I have to select a drawing pen. Okay, we're in drawing mode now. So, I'm going to select a pen. Bobby's Baked Beans have a mean of 16.0 ounces with a standard deviation of 0.1 ounce. Let's label those on this normal distribution. So remember that the mean of 16.0 belongs in the middle. And then every time we increase by 0.1 ounces, that takes us up by one more standard deviation above the mean. So this would be 16.1 ounces, 16.2, 16.3, or if we're on the less than average side, 15.9 ounces, 15.8, 15.7. So if we turned the weight of every can of beans into one of those little grains of sand and threw them on a pile, this is how they would pile up. So we've labeled the x-axis down here with ounces. And remember that when we count standard deviations above the mean on the same number line, those are called the z-scores. So the mean ends up with a z-score of 0. One standard deviation above the mean has a z-score of 1. One standard deviation below the mean has a z-score of -1, and so forth. Now, the given information in this problem was that we have a can of beans that weighs 16.2 ounces. So that can belongs right there on that distribution. Has a z-score of 2. Okay, let's go over to the Durango commute times. These have a mean of 14 minutes, if I remember correctly. And the standard, let me double check that. And a standard deviation of 2 minutes. Okay, so that means that 14 minutes would be right at the mean, and then we count by twos, 16 minutes, 18 minutes, 20, or on the less than average side, we count backward by twos. So these are the x scores representing minutes, and these are their z scores. We're interested in a commuter who took 18 minutes. So that commuter's commute is right here, and that also has a z-score of 2. So that's what these two values have in common. When we standardize their distributions, they both end up with 0 in the middle, and the items of interest in these examples both fall at exactly 2, a z-score of 2. All right, so what about this follow-up question? How would these values compare? The percentage of cans containing more than 16.2 ounces of beans, and the percentage of commuters taking longer than 18 minutes. Let's chart those out on these graphs. So what region of this distribution would be the beans that weigh more than 16.2 ounces? Well, 16.2 would be the cutoff, and the cans that are more than that are farther to the right. So we'd be measuring the area of that right tail. And likewise, with the commuters who take longer than 18 minutes are those that are cut off by this 18 minutes. Z-score equals 2. Longer than means to the right. So it would also be the area of that right tail. So when we standardize these curves, we find that those percentages or probabilities would be exactly the same. So the moral of this story is that we can use a standard normal distribution to chart out any distribution that's normal, no matter what it measures. It doesn't matter if it measures ounces, minutes, miles, or tons. They can all be standardized to look mathematically the same, so that we can use the same distribution to work with all of them. Okay, now let's also take a look at the z-score formula and see how it agrees with this. That z-score formula again was z equals x minus mu over sigma. So you take your score of interest x, you subtract the mean mu, and then you divide by the standard deviation sigma. Okay, so let's copy and paste that and take it over to this example. The Bobby's beans we'll do first. So in that example, we were interested in a can of beans that had a weight of 16.2 when the mean was 16.0 and the standard deviation was 0.1. That's going to end up being 0.2 over 0.1, which is 2. By the way, what would be the units for that? Let's see. In the numerator, we're measuring ounces, and in the denominator, we're also measuring ounces. So those units actually cancel each other out. So the z-score ends up being just the number 2 with no unit on it. And that basically is why we can apply it to any unit, really. Likewise, down here, with these commute times, we are interested in a commuter with a commute time of 18 minutes when the mean is 14 and the standard deviation is 2. Lo and behold, that also turns out to be 2. And again, the units here would be minutes over minutes, which cancel each other out, leaving us with a pure dimensionless number. So that dimensionlessness is basically what enables us to compare any two distributions. So that was an example of how to use the z-score formula to find a z-score when we already knew a particular score of interest x. Now, using a little bit of algebra magic, we can turn this formula inside out, basically. Inversely, x equals mu plus z sigma. This is the version of the formula that we would use if we were given a z-score. We could plug that in right here. and then that would calculate the x-score for us. So we might have to do one or the other of these, or both, depending on the question. The note that I'm making here is that z-scores rescale the x-axis. That's what we saw here. No matter what the x-axis is, it'll always standardize to have 0 in the middle, and then with a standard deviation of 1. And that's the definition of the standard normal distribution. So that's basically the concept behind it. What we're going to do in the next clip, as I mentioned, is we're going to go to StatCrunch and see how it can help us do these calculations.